Yo, 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 what's going on, guys? Reese here from Stoic Pool, and this is the first in a series of YouTube videos I'm going to do about Aiken, the smart contract language, which recently blew my mind. I was writing Plutus and Plutarch before, and Aiken is so nice to use. It pairs really nicely with Lucid, which is what we're going to do. We're going to pair those together so we can build the validators, but then we can still build the off-chain transactions and actually run them in the video, so you can see them working on the preview network, because that's what we're going to be using. Initially, I was going to start super basic, like introduction, a little bit about stuff, kind of bring you up from where Plutus Pioneers leaves off, more or less. But I kind of wanted to start the series with a bit of a bang, so I thought I'd do something a bit more interesting. I put out a tweet yesterday saying, I'm starting this series. Does anyone have any ideas or suggestions? And Jonah responded saying, you should do the Fractionalised contracts. I'm not going to do the Fractionalised contracts, but what we will do is we'll take that concept of fractionalized NFTs or fractionalized tokens, and we'll do something with it. So we'll make an example of a fractionalized NFT contract. There are a couple of moving parts to this, so I'm going to walk you through that first, just so you have like a concept of what we're going to be building and how the process is going to work. So let's get into it. So fractionalized NFTs, it's quite self-explanatory. You have one NFT and then people own tokens, which are like a fraction of a representative of a percentage of ownership. So the way this works is we need a minting validator, minting contract, that's going to mint two tokens, or it's a pair of tokens. And one of the pair is going to be the NFT, the actual asset itself, and then the other side of that coin is the fractions. So we're going to do it with like one NFT and 1,000 fractions. So owning one of those tokens gives you 0.1% ownership in the NFT, and so that's the numbers we're going to go with. When we mint these tokens, we can't just distribute them or like mint them and send them nowhere. Instead, we need a way for people to redeem them so they can purchase a percentage of ownership. And we also need somewhere to, like a little box that we can keep the NFT itself safe so that no one can access it, no one can take it, and you can't accidentally spend it and lose it, because that's, as part of managing that portfolio for people, you need to make sure that you actually maintain control and also that you can't do anything stupid with it, right? Like accidentally. Right, so we're going to have three validators. The first one is the minting policy, which is going to mint the tokens. The second one is a locking validator, which is going to essentially just lock the reference NFT, like the main asset, away so that nothing bad can happen to it. And the third one is a distribution validator, so people can buy or redeem one of those tokens and have a share in ownership of that asset. So now we understand that. We're also going to need to build three transactions. So the off-chain code that actually unlocks, like build the transactions that unlock those contracts so that we could have it on like an interface, and also so that we can just test it right now. So we're going to have the validators written in Aiken and the off-chain code written in Lucid. Okay, so enough of a ramble. Let's have a look. Right, so we're going to start off making a new Aiken project. We're going to call it Frac, and we're going to go into the validators folder and create a frac.ak file. And we're also going to use this lucid init file, which I'll make available. It'll have the block frost stuff, it'll have the validator kind of reading and building, and it also has this function right down the bottom called split UTXOs. What this does is it takes a transaction from your wallet and it creates 100 ADA UTXOs at your address. This owner address is the one we're going to be using, and it's just referenced above as the address of the person who's connected to the instance of Lucid. We're also going to need three other functions, and those are mint tokens, redeem tokens, and update tokens. It's good to know the processes or like the transactions that you need to build beforehand, because if you don't, then you're just kind of building stuff and you have to try and do everything from a concept. It's very easy then to mess it up because you write different logic to what you actually need, because you're just putting it out as you go, quite happy. But then when it comes to actually testing or building the transactions, things don't quite work out how they're supposed to. Switching back to frac.ak, we're going to first put the prefix in for the reference token, which is 100, and we're going to put the prefix for the fraction token as well, which is 444, according to SIP68. And then we're going to make 3 validators. So the first validator is our minting policy. We're going to take a redeemer, a script context, and return a bool. And when r.a, the a field, is 1, it's going to spend, and otherwise it'll spend. Then we're going to make a reference token locking validator. This is going to take a datum, a redeemer, and a script context and return a bool. And when a is 1, it's going to return true, and otherwise it's also going to return true. And lastly, we've got our distribution validator called distro. That is going to take a datum, a redeemer, and a script context and return a bool. And when, you guessed it, a is 1, it's true, and otherwise it's true. Then we're done. So now we've mapped out our validators, we can switch back to Lucid and actually draft the transactions. This is really important because once you have the transaction built, you can test that the thing you want to do actually works with validators that will always enable anything. There's nothing worse than spending like hours working on validators, just cranking out all the logic, only to compile and find out it doesn't work, and then have to go back and incrementally knock stuff out until you figure out where the problem lies. Honestly, it's just not worth the stress. So we're going to start with mint tokens. We're going to create a new transaction which mints assets. It's going to mint 2 different groups of assets. The first unit is going to be the mint policy ID, token name, and the 100 prefix, and we're going to mint 1. And the second one is the same, but with a 444 prefix, and we're going to mint 1,000. Then we're going to add the redeemer, we're going to attach a minting policy, and we're going to pay to 2 contract addresses and complete. The first contract address is the locking address. We're going to add a datum, and we're going to insert that first unit, the first token, the 100 reference. And then we're going to do the same with the distribution validator, add the D datum, and add the reference, the fractionalized tokens. This is the main functionality that we want. This is like the setup of the validators. So if this works, then we're good to proceed and kind of carry on with everything else. For now, we're just going to draft out the others, but we're not going to fill in any of the details. So with redeem tokens, again, we're going to create a new transaction. We're going to collect from the distribution validator with a redeemer. We're going to attach a spending validator, which is also going to be the distribution validator. And we're going to pay to the beneficiary address, the user address, with 1 token. And we're also going to return all of the other tokens back to that validator so that other people can withdraw them as well. And sign the transaction and submit it. Then lastly, we got update tokens. We're going to create another Lucid transaction. We're going to collect from the locking validator with the token and the redeemer. We're going to attach the locking validator, and we're going to pay back to the locking validator with the token. Right now, it doesn't matter what other stuff we do, and we're not actually going to run these transactions yet. We're just going to map them out so that we know the process that needs to happen. We can look at the inputs and the outputs of the transaction, and we can make sure that we build validators that force that transaction logic, because otherwise anyone could do anything to the validator and it's out of your control. We need to control exactly what happens to those validators so that we can force the appropriate behavior. That's the whole point of doing the smart contracts. So now we got that in place, we can start working on the redeemers and the datums and parameterizing the contract. So we're going to have mint action, which is going to unlock a minting transaction. So now we got that in place, we can move on. We can move back to the validators. We're going to do a mint action, which is the redeemer for the minting contract. We're going to take 2 integers and a byte string, which is going to be the token name. We're then going to do the same with the locking validator. We're going to have a lock action redeemer, which is going to be 2 integers, A and B, and the distribution validator is going to have the same, both A and B in the redeemer. We've already put when r.a is 1, it's going to return true. So this is basically the action part of the redeemer for the validators. It's going to check that number in the A field, and based on what that is, it's going to decide how to build transactions. The other thing that we want to do is parameterize the validators so that we can stop anyone else from spending from it. We're going to do this by parameterizing it with our owner pub key hash, which is like the project owner, if you like. And we're going to parameterize all of the validators with that so that they're unique to that pub key hash. And then we can start drafting out the logic. So the distribution validator is going to make sure it has one output and one less asset. Any other case of the redeemer is just going to be transaction is signed by the owner. We're going to do the same then for the locking validator. It has to be signed by the owner in both cases, and the output contains a single token of the policy ID, which we mint. So we're actually going to add the policy ID as a parameter as well. Lastly, we're going to do the same for the minting validator, the minting policy. So we're going to mint 1 times 100 prefix token and 1000 times 444 prefix, which is the fractionalized ones. The fractionalized ones we want to send to the distribution validator, and the prefix 100 we want to send to the locking validator. And we need to make sure the transaction here is signed by the owner, so no one else can mint tokens from that policy. We also, in the other case, we want to allow people to burn tokens. So we're going to make sure, in order to burn, it needs to be signed by the owner, but it also needs to have the reference NFT and all of the reference tokens. You might think, oh, why would we let the guy burn it? Well, there are other cases that people might need to burn tokens other than just rugging a project, and that might be something like they're upgrading or they're changing something about the tokens, or they're bringing them in and they're releasing more tokens, or whatever. We need that kind of flexibility to enable future things to happen, like changes to be made. But in order to make those changes, we need to make sure that the person who's doing it, the owner of the project, can't just burn their NFT, like burn the reference token and screw the community over. Instead, we need to make sure they have the full available amount of fractionalized tokens, so they have 100% ownership of the tokens to be able to burn it. And that's really just a protection mechanism for the users or the community who are participating in this fractionalized system. With these transaction outputs, we say we want to send to the locking validator and the distribution validator, and so you might be thinking, why don't we just parameterize the validator by the locking validator so that you have to mint to the locking validator, we can force it, because that creates a circular dependency. The locking validator is already parameterized by the minting policy of the minting script. So if you also parameterize the the minting by the locking validator, there's a circular dependency, and that basically it means there's no ground zero, there's no starting point for the contract. That relies on this relies on that relies on this, and you just go around forever. So instead, we can't parameterize by the locking validator, so we're just going to remove that, and we're just going to say that it has a single output that has the reference token, and we can worry about the details later. This is actually a really good use case for reference inputs, which is beyond the scope of this video because we're already doing 3 validators. It's already kind of complicated, but I'll do a video about references in the future so that you can understand how they work as well, or how you can use them in your own projects. And then, yeah, it's just another video, all right? Don't worry about it. We're not going to do it this time. So you probably noticed that the transaction signed by owner is like a requirement for most of these options, if not all. Actually, we don't want it for redeeming, but we do want it for every other process in these validators. So this is actually the perfect opportunity to have a helper function, and we'll come back to this, but we'll just put it up here now so that we know that it needs to be made. We're going to call it tx signed by, and we're going to take a transaction, and we're going to take a pub key hash, and we're just going to return a bool. But I'll get to that in a sec. Don't worry about it right now. Just know that it's going to happen. Right, so now we got everything mapped out, we can start thinking about the actual logic. So with our minting policy, we're going to get the script context, and we're going to pull out the fields transaction and purpose, and we're going to expect the purpose to be mint. And from that, we can get the policy ID of the tokens that the validator creates. Then we can get the mint and outputs from the transaction. When we get in the mint, we want to expect that there is a reference asset name and a reference amount, and a fractional asset name and a fraction amount. And we can just take that from the minted value of the transaction. We can extract the tokens or filter for the tokens of that policy ID, and then we can put it in a list. And this is going to give us that shape, like that data structure. And we're expecting that there's only 2 things being minted, so 2 different token names of the same policy ID. And we're going to just make sure that we pair them up with the amounts so that we can check against it later. Before we go any further, we've got to make sure we start importing these things, because trust me, there's going to be a lot of errors later, or warnings with things that have been or haven't been imported. So we're just going to import transaction with the things we've used. We're going to import the value, dict, and list. And we're back to the validator. We're also going to pull out this extra signatories, which is a list of signers. And we're going to make sure that the list has the owner. The owner is parameterized by the script, so it's fixed. And what this is essentially this transaction signed by owner function that we need to build. So we can remove that from the requirements of the other. Okay, now we can start to tackle these transactions. So the first one, we need to expect that from a list of outputs, we have an output with an inline datum, which we're going to extract. We're going to make sure that datum is a token datum, and it's going to an output address. Actually, we can't do the output address, if you remember, because we can't parameterize by the lock-in validator. So instead, we're just going to check that it has one of the reference tokens, and that's it. So now we have our first part of our outputs done. We're making sure that we mint one reference output, or an amount of reference tokens, and that reference token is sent to a single output. Now, we're not actually forcing this yet, but we will be later, so don't worry about it right now, just trust that it's going to be the case. Next up is the fractionalized tokens. Again, we're going to check from a list of outputs. There's one output with the quantity of, and we're just going to specify those specific tokens, and that it's 1,000. This could actually change. We might want to mint a different amount of fractionalized tokens. Maybe we want to do 100 or 5,000 or however many. So instead, we're just going to put this as a variable, and we're just going to check that the variable is the amount that's being sent. That variable is actually going to be in the redeemer, and so it's going to be the B field. And just so you can see, now we have that B field is the number of fractionalized tokens, the byte array here is the token name, and the A field is the redeemer action. The last step here is to enforce the token names. So we're going to make sure that we've got a specific asset name, and asset name is the type of a token name in Aiken. So we're going to say let token name equal of the type asset name equal TN. TN's from our redeemer, remember? Then we're going to say the reference token name is token name and fraction token name is token name. And we're just going to put them in a list here like this. Now this is actually another perfect opportunity for a helper function. So we're going to stick that right up the top. We're going to call it make token names. We're going to give it a token name as a parameter, and we're going to return a list of asset names. Nice and simple. So now we have that, we can say let token names equal make token names, and we can add that redeemer value, the token name value, as the parameter. Sorry if we're going too fast here, guys, but there is a lot to get through, and I want to just brush through everything quickly because this video isn't really for beginners, but it will give beginners a bit of a high-level concept of how structures work, like validator structures work, and for slightly more experienced people or people who've gone through the Plutus Pioneers, they'll hopefully be able to keep up with this and see how everything goes. So we got our, just to recap, we got our mint action redeemer, which has a byte array called TN, and that's the token name. And we're passing that as a parameter to make token names, our helper function, and we're calling that token names. I know I'm saying token names a lot, but it's sorry. So we're going to have a token name prefix, and we're just going to make a list of the reference prefix and the fractionalized prefix, and we're going to map these two lists together. So we're going to map the token name prefix and the token names together, and that's just going to be a function that takes two things and concatenates them. Again, this is a perfect opportunity for a helper function, so we're just going to stick that up the top, call it fraction token prefix. We're going to give it a token name, and we're going to return, we're going to make token names, and then we're going to create the reference prefixes, and then we're going to map them together. We're just going to keep this stuff out of the validator so that it's easy to read, and there's no point in having it in there. It's just going to add a load of clutter to the validator. You can tell from the name of that function what it does, right? So you don't need to stress about that. It's pushing it up there just to save a bit of space and make everything a little neater and tidier. So now we've got a fancy little helper functions. We can make token name list, and we can just call that helper function, and everything will be done for us. Now that we've created this, we need to check what's being minted against this expected behavior. So we're going to create a token name, a fraction token name check, and a reference token name check. And it's basically just going to check that the appropriate values and the appropriate token names have been created and assigned to the right places. Now, this is a good opportunity to introduce you to a little library of helper functions that I built called Okapi. And this is what this OK compare token names is, where you just add the asset name and a list of token names. We're not actually using Okapi right now, so instead I'm just going to build this helper function for you, compare token names, which takes the asset name and compares it to a list, like an index of a list. So we're going to take an asset name and a token name, which is going to be a byte array, and we're going to return a bool. And that's so that reference token check can be true. So with this helper function, we're going to expect a token name called TN, and we're going to make sure that the asset name is equal to the token name. That's it. This is obviously going to be a helper function, so we can stick that at the top, and then we can just use compare token names in our validator. So we're going to put compared token names, and we're going to put the reference asset name and the list. Remember, the reference token is index 0, it's the first element, so we compare it against index 0 of our token name list. And then we'll do the same for our fractionalized tokens, which is index 1 of that list. And we're going to make sure that the reference amount is 1, and the fractionalized amount is equal to the B field of the redeemer. And lastly, we're going to run both of those token name checks. And I realized I put user token instead of frac token, so I'm just going to change that quickly and we'll carry on. So, a quick recap of the validators, just because that was quite quick and there was a lot going on. First, we get the script context, we extract the policy ID from the purpose, we expect a certain amount of mint of that policy ID, and we check that it's signed by the owner. Then we've got our outputs. We make sure that one output has an inline datum of token datum and it has a single reference token, and the other one has all of the fraction tokens. We also compare the token names. Well, we make the token names and we compare them against what's being built, and then we check the amounts are correct and the names are correct. Now, we also need to do this burn functionality. We've already made sure that it's signed by the right person, so all we need to do is make sure that there is -1 reference token and minus all of the fractionalized tokens. Okay, so while we're here, we might as well make the transaction signed by helper function. So we're just going to call this expect tx signed by. We're going to take a transaction, and we're going to take a verification key hash or a pub key hash, and we're just going to do this list check. So we're going to build that helper function now, tx signed by transaction, verification key hash, and check that the list of extra signatories has that pub key hash. That's it. Now we can add this tx signed by to all of the other validators, we can remove the comments, and we're ready for our first test. Quickly, before we do that though, we actually don't want the distribution to require a signature from the owner key, because otherwise the poor guy who owns the project has to be signing every transaction that comes in that when people are trying to redeem it. That's 1,000. What if they're doing 5 at a time? It's impossible to manage. So we're going to remove that for now, and we're just going to let anyone redeem tokens. We've got a bunch of import problems, so we're going to import a load of stuff. I'm going to skip through that because you don't need to see it, but just trust me, you need to make sure everything's imported if you're using it, because otherwise it doesn't know what that thing is, right? We also don't have a type for this verification key hash, so we're going to just build that quickly by hashing a verification key, and now we're good to go. And yes, Aiken, I did mean policy ID, so thanks for that reminder. I also forgot to build the datums earlier, so we're going to do that quickly. We're going to have a token datum. Token metadata needs like a name, an image, or like a type, source, and a media type. So we're just going to put that in. We also need the distribution datum, so we're just going to build that type quickly. It's going to be an int, and that's it. One thing I missed actually is this option problem. So right now it's expecting a byte array, but it actually is an option byte array. Right, we got 5 warnings, but it's just because we're not using stuff yet, even though we've specified these types. So we're not going to worry about that. We're just going to clear the terminal and run aiken build, which is going to compile the validators for us. It's going to stick it in this plutus.json file, and there's a bunch of stuff in here, but the only thing we really care about is these validators. So we can close this preamble. And in our validators, we've got a bunch of parameters and other things that have been specified. We're just going to close all this up because we don't need to worry about it right now. We just want to have like an easier look at the things we need to see. And the thing that really matters here is the order of the validators, because that's the index we're going to need to import into Lucid. So we're going to need to make sure that we know the order of the validators. We've got our minting validator last. So we're going to have our minting validator, then our locking validator, and then our distribution validator. Distro is index 0, lock is index 1, and mint is index 2. So in our Lucid file, we can now start importing these validators so that we can test the minting transaction. Right at the top, we got our owner pub key hash, and we actually need to run this first because it's a parameter. So we need to get that value first. Then we can start to create the functions that read these contracts and apply the parameters to the code. We need to make sure they're done in the right order. So lock needs to be after finding out the minting policy ID, because that's also added as a parameter to our contract. So we need to make sure that's compiled first. Then we can check for the necessary parameters for the other contracts. We've got the pub key hash for everything, and we just make sure that we put the policy ID in the right one. We can build our function or our transaction execution functions now. We're going to create one called mint tokens, and that's going to mint the tokens. And that will just be assigned to the Lucid function below that mints. We're also going to log the transaction hash and the policy ID of the contract. And then we're going to make one for distribution so that we can execute that distribution transaction and return that transaction hash. And we'll do the same for update tokens as well. We'll return the transaction hash. A quick recap of our transaction we built. We've got the locking address, the distribution address, the locking datum and distribution datum, which we haven't yet put together. We're going to quickly comment out these other transactions because right now we're just going to focus on the minting transaction. And we need to get these values ready so that we can finally test this. We've got our token name, Stoic, and we got our redeemer built, which is a new constructor with two integers, A and B. A is 1, so that means we know we're going to run the appropriate transaction from the contract, but we're also going to create this mint redeemer because there's other information needed. So we're going to just put the same stuff in, with the second integer being the token value, the 100 fraction tokens, and we're going to add the token name. And then we're going to change, because we're doing fractionalized tokens, I'm changing the token name from Stoic to Stoic for fractionalized, right? Even though it does sound like I have a speech impediment. And we're just going to change the redeemer in the transaction to mint redeemer so that it's using the right one, because otherwise it won't work. Okay, now we can do the validator details. We get the address from the locking validator, we'll do the datum for the locking datum, the distribution address, and the distribution datum. To do that, we use lucid utils validator to address, and we stick the lock contract in. And for our datum, it's going to be a new constructor with a name, an image, and a media type. We don't actually have these things built, and for the sake of testing it, we're not going to bother. We're just going to change this instead to an integer, and we're going to use a totally random number, 420. And we're also going to change the distribution datum to the same. It doesn't really matter, but that's what we're going to call it. And we obviously get the address for the distribution validator as well. With that in mind, we're going to remove this token datum. We're going to comment that out, and we're going to change it just to an integer for easy testing. And then we're going to have to recompile the contracts. We're actually going to call the token name Stoic01 because we're going to run these transactions a couple of times. So we're going to increment that value so that we can see which ones are which. And so now we're ready to actually run the script. Well, we're going to make sure it's the right name for the file. Then we're going to grab that command and we're going to run it in the terminal to test the transactions. And we get an error. The reason we actually got this error is because we didn't import our Blockfrost API key, but I'm not showing you what that is, so just put your own in. And we get another error. And this time it's because I can't spell. So we're going to go back here and we're going to write attach minting policy. Hopefully now everything's right. We run it again and we get a redeemer error. The reason we get this error is because we expect this transaction to be signed by the owner. So we need to make sure we add the signer key of the owner pub key hash. Run it again and we get this transaction hash and a policy ID. So we minted the fractionalized NFTs. We can check this transaction hash in Cardano scan, just pop it in and we can have a little look at the transactions. We got stuff coming in, stuff going out. We got 1 reference token and 1,000 fractionalized tokens, just as we wanted. So now we got that in place, we can test the others. So we need to actually add a little bit more info. We're going to make sure that we're distributing the fractionalized tokens. We're going to check for those UTXOs to the fractionalized token and get the first one. There should only be 1. And then we're going to make sure that the out value is 1 less than the in value so that someone can redeem a single token. We can then console log this value so that we see how many are going in. We can add the redeemer to collect from those UTXOs. We can attach our spending validator, and we can make sure we pay to the beneficiary address with just a single token. We also need to make sure we're returning to the distribution validator the rest of the tokens. Now we have that in place, we can just uncomment that transaction and we can run it. So we run the script again. It shows us how many tokens we have. And then we get our transaction hash with our token being distributed. We can check that in Cardano scan as well, and it's not come through yet. Transactions sometimes take a while to actually show in the explorers, so just give it a sec and it'll come up. While we're waiting for that, we're going to update the tokens. We uncomment the token transaction and we can work on this update tokens function. We're going to get the UTXOs at the locking address with the unit. We're going to extract the head of that list, and we're going to console log that UTXO, and we need to change the datum so that we update the metadata, because that's where the metadata is held. So we're just going to give a new constructor and we'll just change it to a totally random number. Then we add the locking address, we add the new datum, and we add the token back in to make sure that we're spending that back to the validator, because we don't want to allow it to be spent anywhere else. We don't have the logic built there, but that's going to be how the transaction behaves. So we'll just do that now so that we know that the right functionality is there. The last thing we need to do is add the signer key. We'll make sure we do it this time, and we should be good to go. But first, let's just check on that transaction. We can see here on Cardano scan, we've got our 1 token coming out. We've got 1,000 tokens coming in. We've got 1 going out and 99 going back to the contract address. So we run the update transaction and it shows us the transaction with our reference token. And when it goes through, updated NFT, and we can grab that transaction hash and check it. You can see here there's a token going in and a token going out, and the datum has changed. So we know that we have updated the metadata of that reference token. We need to make sure that we can't redeem more than 1. Right now we actually can, so we're going to test that just to show that it does work, and we're going to use another totally random number. We'll run the script and we'll see what happens. Okay, so that worked. So we'll grab the transaction hash and we'll check it in Cardano scan. You see that 69 tokens have been withdrawn. 999 going in, 69 going out, and 930 being returned. We're going to change that back to 1 because I think you've realized by now I make a lot of mistakes and forget to do things, so we'll just change that before I get ahead of myself. And we can start working on the logic for the distribution validator so that we can force only a single token can be removed. So we've already spent a lot of time writing the minting validator, and I don't want to spend loads of time going over the same kind of code functions, like building the same kind of functions over and over. And this is actually a perfect time to introduce a library that I'm working on for Aiken called Okapi. And it's called Okapi so we can say, okay, whatever the function is, and it basically will help make this whole process a lot easier. So we're going to use some of these helper functions so you can kind of see how it works. We've already built some helper functions, which are all in that library. We're just going to import it and work with these things now to make building the logic for the locking validator and the distribution validator just much quicker. So we're going to remove the true, and we're going to say let out equal okay get singleton output. That means there's only 1 output. We're also going to get our own input, and we're going to say, okay, has 1 singleton asset less. So that means it has 1 asset less on the output than it does on the input. We're going to pass our in value and our out value as parameters. We're going to make sure that we actually import Okapi as okay, so that we can call these functions, and then we're good to go. We're going to run aiken build to recompile the validators, and then we're going to uncomment the mint and the update token transactions. Now when we run the Lucid Code, it will sequentially go through all 3 of those transactions so that we don't have to do each one individually anymore, because we know that they work, so we can just run them all together. So we then run the code, we see our mint, we see our distribution, and we see our update happen successfully. Now just to make sure this does work properly, we're going to change the withdrawal to 3, and hopefully when we run it, it fails. We're going to comment the minting and the updating so that we don't do it twice. And we're going to run the script, and you can see here this redeemer error. This Plutus error means that it failed. We're going to change those 3s back to 1s, and we're going to try withdrawing the token again. That was successful. We can check that transaction hash if you want, but I don't really think there's any need at this point. We're just going to get on with the rest of it. So the last step is to write the logic for the locking contract. Again, we're going to use Okapi for this, so we're going to say, okay, contains single token of in our out value. But to actually do that, we need to make sure that we get our own output. So we're going to say let out equals okay get own singleton output, and then we're going to pass that to contain single token of. We're going to try and build it and realize I've made another spelling mistake. Rebuild, and then when we run it, we'll see all 3 transactions come through successfully. The final step really is just to tidy up the code, remove all the comments, and just organize everything a little bit nicer. We'll uncomment the transactions, and we're done. Okay guys, that's it. So it was fast and it was complicated. Hopefully you followed along all right. And just to recap quickly, we made a minting policy that mints the fractionalized token and a reference NFT, like the actual representation of the asset. We've put the asset in a locking contract for that we can only spend to update the metadata, and it has to go back in its place. And the other thing we did was made sure you can only redeem 1 of the fractionalized tokens per transaction. Guys, this was complicated and we did whiz through it. I'm going to start doing some more easy and more beginner-friendly versions of these kinds of videos, but I really wanted to start off with a bang, like I said, so I wanted to explain something like this, and the example that Jonah suggested actually was perfect, because it shows how smart contracts work together to build out the logic that's appropriate for whatever function that you're trying to achieve. So when I'm going to make this available on GitHub, so I'll pop a link in the description, check it out. You can download this code, you can run it yourself, and if you have any questions or comments or anything, pop them in the box. If you have any suggestions for like future videos or anything you'd like me to cover, pop them in the comments below or reach out to me at Stoic Pool on Twitter. Do all the YouTube stuff, you know, like subscribe, blah, 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 share it, and I will catch up with you in the next one. See you then.